Good morning, everyone. Thank you for being here, or afternoon. We are honored to have this seminar today. Welcome to the IFE Living Lab Another Hub seminar from the Institute for the Future of Education. We created this seminar as a space for co-creating new initiatives, new experimental or database calls for research. And in this occasion, we will have the presentation from Dr. Roland Molontay. How can data science assist decision-making in higher education? Professor Molontay is assistant professor at the Budapest University of Technology and Economics. He's founder and director of the Human and Social Data Science Laboratory. His research focuses on network theory and on data-driven educational research. He's author of more than 30 scientific publications, a regular speaker at renowned international conferences, and the recipient of numerous professional awards, including the Gyula Farkas Memorial Prize. Thank you, Professor, and welcome, and please share with us your talk.
Thank you very much for this kind introduction and also the invitation. So let me share my screen. I hope that it will work. So now you can see my screen and only the first slide. Yes?
Yes.
Is it all right? Yeah.
Correct.
Okay. Correct. So thank you very much once again. It's indeed a great pleasure to be here. So thank you for the organizers for the opportunity to be here. As Professor Ceballos mentioned, I am Roland Molontay, and I am an assistant professor at the Budapest University of Technology and Economics, Budapest, Hungary. And I'm also the founder and leader of this newly established lab called Human and Social Data Science Lab. So this lab works with quantitative methods, and we try to answer questions arising in humanities and social sciences, in particular in education. So one of our aims is to assist decision-making in higher education. And this is what I will talk about. Just a remark that this talk will not be a traditional research talk in the sense that I won't go into technical details of the papers and of the research that I will present. I will just glance through some of the recent research, I would say rather superficially. The goal is to present the big picture, so how data science can assist decision-making in higher education, or at least what we think at the Budapest University of Technology and Economics, how it can assist. So I will just rather present the big picture just to give you a taste what we are doing. So let's get started. So as I mentioned, this is the Human and Social Data Science Lab that I'm from. And our mission in this lab is to translate fundamental research in data and network science into lasting impact in social sciences and humanities. We both conduct methodology-oriented basic research in network science and in data science, and we also apply these methodologies with a human-centered and societal focus. Basically, our research revolves around four main topics: network science, educational data science, this is what I am going to talk about in more detail, health data analytics, and intelligent monitoring and anomaly detection. If you are curious about the other three areas, then I recommend our homepage, the hsdslab.math.bme.hu. So the topic for today is educational data science. Basically, a couple of years ago, many researchers discovered that there is great potential in educational big data. In particular, there is great potential in the big data stored in the educational administrative systems. So basically 10 or 20 years ago, the data was stored in the educational administrative systems, but not analyzed, and no insights or no knowledge was extracted from this data. But a couple of years ago, many researchers discovered that it makes sense to use machine learning methods and data science methods on educational big data to extract knowledge. And this field of research is called educational data science. It's internationally a quite established discipline, multidisciplinary or interdisciplinary discipline. In Hungary, there is also an increased interest, but I can say that in Hungary, we are kind of pioneers in this field of research. So let me mention how it started, because it's not that easy. I mean that, okay, we have the data, we are a quite large public technical university in Budapest, the capital city of Hungary, with more than 20,000 students. And of course, we store lots of data of the students, of the professors, of the courses. So we have lots of data in the educational administrative system. Okay, but okay, this is just a data tom. So I mean, no analysis was done on the data. And 5 years ago, we initiated a collaboration with the Central Economic Office. So basically, the Central Economic Office is the owner of the data. And we as researchers at the Institute of Mathematics, we asked whether they would be interested in a collaboration when so they have the data, we have the knowledge, we have the mathematical or machine learning expertise to analyze this data. And they were kind of open to this collaboration. So we initiated this project with the aim of supporting educational data, educational decision makers. So using insights that can be covered, that can be discovered using data science and machine learning methods to help the decision makers. Another problem came up, of course, that this data is kind of sensitive. So, and in the European Union, we have kind of strict policy of how can we access data, personal data, and so on. I'm not sure whether you are whether you heard about this GDPR. So this is the General Data Protection Regulation of the European Union, and it's very strict. So we have to also be in line with these regulations. So of course, all the data is anonymized, so no personal identities can be discovered using the data. And we also have strict non-disclosure agreements. All the researchers who are working with this kind of data must sign these NDAs. Okay, so after we did this, this administrative stuff, we can start doing the real research, the real analysis. And one of our first papers was about the predictive validity of the university entrance score. So what is it all about? The admission procedure in Hungary is going as follows. So students have a preferential ranking of the institutes of the universities. So there are many universities in Hungary, and they rank the universities, or rather the programs, the undergraduate programs, according to their preferential ranking. Okay, but of course the quotas are limited, so not everybody can gain access to the place that he or she wants to. So the universities, the programs also rank the students according to the students' abilities or something like that. Basically, the university programs, the ranking of the university programs, so how the university programs rank the students is according to their so-called university entrance score. That is a composite score many pre-enrollment achievement measures, such as high school grades and the grades of the school leaving examinations are in this composite university entrance score. And our question was that this university entrance score measures well or not, whether it has the ability to distinguish between students with low potential and to distinguish between students with low potential and high potential. Because if that is the case, then this university entrance score has a high predictive validity, and it's a good thing. And we found out that yes, it has a pretty good predictive validity in comparison with other scores or other tests that we used previously, or in comparison with international international comparison. In this figure, you can see on the x-axis, you can see the admission point score, and on the y-axis, you can see that how many students we admitted or are there at our university in that university or admission point score range, and what ratio of them are graduating and what ratio of them dropped out. And we can observe that the higher, that's not that surprising, that the higher the university entrance score is, the more likely that the student will graduate. And this is quite significant. So it has a significant predictive validity. On the other hand, we also found some interesting things about that. So, for example, we found that the predictive validity of the university entrance score varies over disciplines. So, for example, in engineering and natural science fields, the score has a much higher predictive validity. So it's a better predictor of the future academic performance, for example, measured, for example, in dropping out or measured in the degree grade point average or whatever, than in economics and social sciences, for example. So in social sciences, the predictability is not that strong. That's one thing that we discovered. We also discovered that the university entrance score overestimates the performance of male students. So that's strange that at our university, male students come with higher scores, higher university entrance scores, but they graduate less likely, and they graduate with lower degree grade point average. So they high school achievements or what the university entrance score is based on is higher, but still their university performance is lower. That's why the university entrance score overestimates their performance. We also discovered that the general knowledge is more important than the program-specific knowledge. So in this university entrance score, so we are a technical school. The vast majority of our programs are engineering majors, but still not only mathematics and physics grades have high predictability in this composite entrance score, but humanities, so for example, Hungarian language and literature or history, these are also very important subjects that have high incremental predictive power over the mathematics result or over the physics result. And we also discovered that by some slight changes, it can be improved. So I won't go into details because you are not that interested in the Hungarian system, but using some slight changes, it can be even improved. So that's, for example, one example that how data science can really help in this. It has managerial implications, or it has real implications that what is a good composite measure, composite score of the university entrance score that has a high predictive validity, and we examined that. Or another study, we investigated whether the at-risk students, so students at risk of dropping out, whether they can be identified early or not. So based on historical data, so that's basically a supervised learning task, a binary classification task. We would like to predict whether the student will drop out 1 or graduate 0 or so something like that. So a binary classification task. We have the training data, the historical data. So on the historical data, the machine learning algorithms can learn the pattern, who are the ones who are at risk of dropping out. And we do that based on the data at the time of enrollment. So what data we have at the time of enrollment? Basically, we have the sub-scores of the university entrance score, of the admission point score. So basically, these are the high school grades. Basically, these are the results of the school leaving examinations called Matura exam in Hungary. We have data about their language certificates, so what foreign languages they can speak. We have data of their high school, so which high school they attended, at which town, whether they are males or females, how old they are, and so on. So based on these data, we can predict with quite of good predictive performance at-risk students. So kind of efficiently, they can be identified solely based on the data available at the time of enrollment. Of course, the question comes up whether the predictive power can be improved if we also include data that can be measured during the first semester. So previously, we only used data that is available at the time of enrollment. And our next question, whether the predictive power can be improved if we add additional data, namely the data that we measure during the first semester. And of course, that's not that surprising that the answer is yes. The first semester performance indicators have significant incremental predictive power over pre-enrollment achievement measures on student dropout. So that's, of course, not that surprising. Maybe that's more surprising that given the first semester performance related attributes, pre-enrollment measures have only little incremental predictive power. So if we solely rely on first semester performance related attributes, that adding pre-enrollment achievement measures only have a little incremental predictive power. So it suggests that the predictive power of high school achievements basically incorporate into first semester performance measures. So that's another finding that we had. Next, the question comes up that okay, that's kind of cool that we have these machine learning models, black box models that will predict who are the students, who are at risk of dropping out. But the questions comes up that okay, we can identify that okay, John will probably drop out and Susan will probably graduate. Okay, but what to do with this information? And here our answer is that we should interpret these black box models. So we are not satisfied if we have a well-performing machine learning model with a high AUC value or with a high precision, high recall, high accuracy. That's very important. That's indeed very important. But we go one step ahead. And that's the so-called interpretable machine learning or explainable AI, XAI. That's kind of a new and hot topic of machine learning. So we would also like to interpret the results. We would like to also answer the whys. So not only that, okay, he or she is identified as at-risk student, but why? Why do we why do we say that he is at risk? And we will measure the so-called marginal contribution of the variables to the prediction using the game theoretical concept, the Shapley value or Shap value. So if you're familiar with the Shapley value, then the gain here is, that's a game theoretical concept, as I mentioned. The gain here is reproducing the outcome of the model, and the players are the features in the model. And so that's how the Shapley value can be calculated. So here we can see the formula, but you don't have to worry about that. The point is that using the Shapley values, we can locally interpret the results. So not only globally, so we can not only say that globally this is an important feature. So globally, I don't know, the high school mathematics grade is a very important feature. But we can also say that locally, using this individual, what were the important features? Let me illustrate it with an example. So here we can see 3 students with their output values and with their features that contributed positively or negatively to the prediction. So for example, the first student is an at-risk student because the output value is 0.16. It means that the estimated or predicted probability of graduation is just 0.16. So he or she is indeed at risk. But also I will also tell you the whys. So here you can see the blue and red colored I don't know, segments. And the width of the segment corresponds to the importance, the Shapley value of the feature, and the red segments are the ones, the red features are the ones that contribute positively to the prediction. So push the prediction higher, and what is written in blue, those contribute negatively to the prediction, so pulls the prediction lower. So for example, if you look at the first student, we can see that the mathematics score is just 62. The fact that the mathematics score is just 62, so it means that in the mathematics mature exam, the student obtained just 62%, contributes very negatively to the prediction. So that is the most endangering factor. Okay, the fact that his or her average science subject high school grade was just 3.5, that is the second most important variable that also contributes negatively to the prediction, and so on. We can see that there is a so-called years between variable. This years between variable basically measures that how many years elapsed between the graduation from the high school and between enrolling in the university, and that score is 0. So that's good because based on the data, those students who enroll in the higher education immediately after leaving high school graduates more likely than those who have gap years. So that contributes positively to the prediction. Now let's take a look at the second row. The second row corresponds to a very talented students, let's say, because so that's a strong student. We can see that almost all the factors are red. So almost all the factors contribute positively to the prediction. We can see a very high mathematics score. We can see a very high score in the elective subject, and so on. So every score contributes positively to the prediction. Maybe more interestingly, the last student, the last row, that's a borderline student because the output value is 0.5 or 0.52. So that's in between, we are kind of uncertain. So that's a 0.5 probability of graduation. And we can see that the students' good mature scores push the prediction higher. So he or she has a good score in mathematics and a good score in the elective subject. On the other hand, the fact that 2 years passed between the mature exam, the school leaving examination in high school, and the university enrollment together with his or her satisfactory 3 high school grades in Hungarian language, push the prediction lower. So that those are the factors that are in blue. So I think that's kind of handy, and that adds that has a real added value. So beside outputting the prediction, we also interpret the results using these SHAP values, explainable artificial intelligence. Next, we also looked at traits. So here, kind of, that's a catchy phrase, traits or grades. So far, we concentrated on grades because pre-enrollment measures, pre-enrollment achievement measures, mostly grades, so high school grades and master exams, school leaving examination results, and first semester achievement measures. So we concentrated on achievement measures. And based on the achievement measures, we wanted to predict the dropout. But here, we also take into consideration psychological factors. Of course, the problem is that we do not have data in the administrative educational system of the student's psychological profile or psychological factors or traits. But using some psychological tests or surveys, we measured some, okay, so that was not for all the 20,000 students at our university, but for a few hundred students participated in this survey, and we measured their psychological factors. And we were curious whether these psychological factors, the psychological profile, has incremental predictive power over the grades, over the pre-enrollment achievement measures on dropout prediction. So using the traits, can we achieve a higher dropout prediction performance? And the answer is yes, that using an appropriate set of psychological measures, the dropout can be predicted significantly better than just solely relying on grades. For example, coping proved to be the most important psychological factor that sheds light on the importance of stress management for university students. And what is maybe even more important, that some of these psychological factors can be improved. So if we identify that, okay, early on, that, okay, so maybe this student is in danger, is at risk of dropping out because he or she has a low coping skill, then we can offer targeted development, we can offer other assistance to the student. So because these competencies and skills can be efficiently developed. And here we arrive on this very complicated question that I basically touched upon a little bit, that how to use the results. So okay, we gain the knowledge, we extract the knowledge, we extract the insight. Okay, we know that these students are at risk. Maybe we also know that why, using the, as I mentioned, you remember, using this local interpretation, we know that, okay, this student is at risk of dropping out because he or she has a low score in mathematics. Okay, that's what we know. But how to use the result? Because that's something very important. And of course, this is a complicated ethical issue. I usually tell jokingly that, of course, that's not a good utilization of the result if we go to the student on the 1st of September, when he or she registered on his first day of school, of the university, that, okay, hello, John, nice to meet you. We are from this prestigious university, and thank you very much, and congratulations for your acceptance. But we have some very clever machine learning algorithms, and the machine learning algorithm predicted that you won't graduate. So that was a nice try, but okay, so goodbye. Of course, that's not a good utilization. But okay, then the question comes up that how? We don't like these self-fulfilling prophecies, so we would like to avoid that. that's what I mentioned basically. So we could, if we identify that, okay, this student is at risk because she or she has a low score in mathematics, then we can offer a mathematics remediation. Or if we find out that he or she has a low coping value, you remember that's the psychological factor, we can also offer some targeted development. And what is maybe even more important, that we can we can take one step back in the backward direction. What do I mean by that? What if we use these results to guide students in high school? Because high school students also have the pre-enrollment achievement measures. We can also measure the psychological traits. And based on that, we can basically guide those students whether, okay, maybe mechanical engineer is not really for you, or if you aim for mechanical engineering, then it seems that you should improve in mathematics, because our machine learning approach predicts that you won't be that successful in mechanical engineering because your math result is not as good as it should be. And then we can orient these high school students that I think has a good as a strong added value. So so that's what I wanted to tell about basically dropout prediction. I don't know whether I have time for some other topics, or I should stop here.
Thank you, Roland. A very nice presentation covering all the important aspects of the problem. Congratulations for your work. It's very impressive, and give us an overview of what is the problem we are dealing with at the student dropout. I will open the space for questions. Gerardo is taking note of the questions. If you could please select some of them, for example, from Andres Gutierrez.
Surely, no problem. Actually, we have right now 3 questions that have been put in the chat box. So I will start with the first one asked by Andres Gutierrez. He asks the next question. Why not use white box models like linear regression or decision trees instead of the models that you are using?
Yeah, very good question. Very good question. So why not use white box models? Yeah, that's also an option. The problem is that using the more sophisticated black box models, such as gradient boosted trees or other ensemble methods, we can achieve higher performance, higher predictive power. So the AUC value, the precision, the recall, all these scores are better using more complex, more complicated models. So we would like to have the advantages of both models. So I mean, from both worlds. So the high performance, high predictive performance of the black box models and the interpretability of white box models. And that's why we use these so-called model agnostic tools that can be such as shape value or LIME. That's another model agnostic local interpretability tool to interpret the results. So basically that is the answer for that question.
Okay, so now we're going to go for the next question. Isabel Hilliger wants to know what type of interventions have you implemented based on this data, if any, so far?
Yeah, that's also a very, very good question. So, so we are researchers, and one of our ultimate goal is to publish nice papers in Q1 journals, and that's one of the things that we like. But of course, as I mentioned, we would really like to have real impact and really assess students, really assess decision makers. So that's why we did 2 things. beyond the publications, beyond writing up the publications, we also developed some web applications. And using this web application, both the educational decision makers and students can basically play with these models, and then they can see what the predictions are. So that's one thing. I know that's not an intervention, but still it goes beyond just the publication. So to make these web applications available. And the other thing, yes, interventions. We experimented with offering mathematical remediations for those who are at risk of dropping out, and for those who the machine learning algorithms identified that the main reason of being at risk is the low mathematics score. So that's what I can mention. But yeah, so that's difficult because it's a big university. We have to convince the high level educational decision makers that it is worth doing something. So yeah, we are in the process, in the procedure, I would say.
Okay. Well, we have a few more questions for now. Jose Gerardo Moreno would like to ask about, in the predictive model, what is the most representative statistic variables, like the higher scores? Like, what are some kind of data that results interesting for you in these statistics?
Yeah. So basically, these let me show you here. So using these local interpretations, we can not only tell what are the variables that are the most representative globally. So, but we can also have some insight on what are the ones that affected the local prediction the most. And as you can see here, so for example, mathematics, the mathematics measure school leaving examination score has a high predictive validity, high predictive power, because it seems that it is kind of an important variable. Sometimes if it is low, it pushes the prediction lower. If it is high, it pushes the prediction higher, and so on. So mathematics, the mathematics result was found to be very important. That's not that surprising because, as I mentioned, we are a technical school, we are an engineering school. On the other hand, as I mentioned, humanities and Hungarian language and literature, history, they were also kind of important, so, or at least had some incremental predictive power. And another important thing was this years between variable. Do you remember what this years between variable is? This is that measures that how many years elapsed between the finishing high school, so graduating from high school, and starting the university. So it seems from the data that having these gap years contribute negatively to the graduation, to the likelihood, to the probability of graduation.
Okay. We have another question from Carmen Ortiz. She asked, have you made predictive models on job opportunities for college graduates with performance data during their college?
Extremely good question. So yeah, that's what I wanted to do and I want to do. The problem is that unfortunately we do not have data about that. So so the point is that what I really like about this, that basically all this research, except the traits versus grades, because in the traits versus grades we also measured some additional psychological factors. But apart from that, all of this research is based on the data that is immediately available at the university's administrative system. Unfortunately, the job, so the future, the job opportunity is not available in the administrative system. I know that, of course, this data exists because, I don't know, for example, the National Tax Authority, of course, knows everything about everybody. I mean, they know that which job the student have or had, and what were the employability, and is based on their salary or whatever. So this data does exist, and we would like to gain access to this data, but not yet, unfortunately. But that's also a very good question.
Okay, so we may go, actually, we have only one question left. It's also from Jose Gerardo Moreno, who asked about your university. Do you have some information about the dropout rate before and after and during the pandemic? Like, how is the data change?
Yeah, so we observed something very strange, maybe, or maybe not that strange. So the grades, so okay, you all know that during the pandemic, all the world was moving to distance learning or online learning, and all the exams, or at least half a year ago, and all the exams were in the online sphere. So that made it, I mean, much easier to cheat on exams. So I don't know what is the situation in Mexico about cheating, but Hungarian students, I mean, they kind of take the advantage, or took the advantage of this. That okay, I mean, that's how it works. That in the online sphere, it is easier to cheat. And so, for example, of course, the subject, the first semester mathematics subjects, the calculus subject, this is the subject that I mean, has a kind of a big portion of fail grades on the first semester mathematics subject normally. But during the pandemic, when we had the online system, this failing rate, so the course completion was as high as never before. So that's one factor. And the other factor, of course, is that there are some students who fed up with all these online learning, and they feel that that's not for them, and they cannot follow the lectures as efficiently as they could have followed previously, and they decide to pause their studies, basically, or to have a stop. So we have these two things that has opposite effects. So yeah, that's what I can tell about that. Yeah. So Ahiram Cruz asked about the complete paper. So I mean, all the papers. So these are distinct papers. So if you check our web page, the hsdslab.math.bme.edu, then okay, I will just include it in the chat. Okay. So just 1 minute, I will.
Yeah. Or if you could share your slides with us, we could send it to the assistant.
Yeah, that's also totally fine. But my colleague will send you the link. I just asked him to.
Okay, perfect. Thank you very much.
So here you can see all our publications in educational data science. So if you click on the link, you can check. If you don't have access, because some of them are hidden under a pay wall or whatever, then just drop me an email, and of course I will send you the copy.
Perfect. Thank you very much. Thank you, Roland. Thank you, Gerardo. Thank you very much for your very interesting questions. I will let Joanna to make an announcement regarding the call that we'll be presenting in the coming next week. Let me share again the slide.
Yeah, thank you. Good morning, everyone. Thank you very much, Dr. Roland Molontay, for such an interesting presentation. We share with you that Dr. Molontay and Dr. Isabel Hilliger are members of the advisory board of the call for proposals, bringing new solutions to the challenge of predicting and countering student dropout in higher education. The objective of this call is to deal with the student dropouts, applying machine learning algorithms. Therefore, through this call, interested researchers may have access to the data set and the advice of one of the members of our advisory board to propose new solutions. The call will be published on Thursday, December 16 and 4 p.m. Mexico time, and the 8th International Conference on Education Innovation during the panel Advantage, Limitations and Perspectives of the Use of Educational Data Mining in Measuring the Impact on Higher Education. For more information, please to go the link of the bottom of the slide. Thank you.
Thank you, Joanna. Thank you all. Gerardo is going to share a survey to know what do you think about the topic. Feel free to comment or send us your comments in the survey, and we will be delivering the video recording in an email on next Monday, probably, or before. And thank you for being here, and we'll be also letting you know about the events we will have in the International Conference on Educational Innovation that will be taking place in Monterrey, but also accessible online in the next week. So thank you very much for your contributions. Thank you very much, Roland, for your presentation, and see you in the next seminar in January. Thank you all. Have a good day.
Thank you very much. Have a nice rest of the day. See you.
Thank you. See you.
See you around.
Yeah.
Bye.